So next we have Kumar Gupta. So Kumar will talk about black hole entropy and quantum information scrambling. Go ahead.
Okay, so I would like to start by thanking the organizers for inviting me and congratulating Bal on his birthday. So let's see. The topic is black hole entropy and quantum information scrambling, and this work was done with some people in Kolkata, Supriya Ghosh and Sashi Srivastava. So the plan of the talk is following. First, I'll give an introduction to a brief introduction to the subject. I don't think this audience needs any big introduction. Then I'll describe a model by Raphael, which was originally introduced by Raphael Sorkin, but a time-dependent version of that. Then we will talk about the solution of the time-dependent simple harmonic oscillator, which is relevant for that particular model. Then discuss entanglement dynamics and information scrambling via OTOC, and then we will make some concluding remarks. So one of the main motivations of this talk arises from black hole physics, in particular the description of black hole physics which was proposed by Raphael Sorkin. So a black hole horizon provides a bipartition of the space-time into an exterior and an interior. And with respect to the exterior region, the black hole behaves as a thermodynamic object. This is a well-known thing. And the Bekenstein-Hawking area law gives the entropy as proportional to the area of the horizon. Now, what was this was the standard lore, and then Raphael Sorkin, as far as I know, he was the first person in 1986 who suggested that this thermodynamic entropy, or the entropy of the black hole being proportional to the horizon, could be interpreted as an entanglement entropy. So this was indeed an extraordinary suggestion, and which was repeated by Srednicki later in 1993, and these are the two seminal papers by Luca Bombelli, Ravinder Kaul, Juhan Lee, and Raphael Sorkin in 86, and then followed by Srednicki in 1993. But most of the stuff that Srednicki discussed was essentially in Raphael's paper. Okay. So Raphael calculated, although Raphael's paper talks about black holes, but in reality, this particular publication doesn't use much property of black hole at all. It gives, in fact, Raphael himself says this by evaluating this contribution in a simplified case. So the simplified case is what makes it tractable, and he and his collaborators essentially calculated the von Neumann entropy of a bunch of harmonic oscillators under bipartition. Okay, so it's a purely Gaussian model, and they made a bipartition and calculated the von Neumann entropy. And in the continuum limit, the whole of R3 was bipartition, and the boundary area was denoted by A. And what they found was that the entropy is proportional to the area divided by L square, where L is a ultraviolet cutoff. So as you can see immediately that if you remove the ultraviolet cutoff, the entropy diverges. And this kind of divergence of entanglement entropy, at least in the physics literature, to my knowledge, was first found by Raphael Sorkin. Nobody found this before him. Now, what is the meaning of this divergence? This has become a topic of discussion in recent literature, thanks to several papers by Witten, who claims that this particular divergence that Raphael found has something to do with some deep structures of algebraic quantum field theory, which Bal has emphasized also many times. It has to do with certain properties of algebras observables, for which I am not an expert, so I am not going to go into that details. Although I must say that there are other papers also recently which claim that this ultraviolet cutoff, the ultraviolet divergence is really independent of the issues that arise in algebraic quantum field theory. So there are other papers which say that there are two sources of the divergence of the entanglement entropy. One is coming from this ultraviolet divergence, the other is coming from some mathematical properties of algebras of observables in algebraic quantum field theory. Now, I cannot honestly figure out which is the right answer, but this is a discussion which goes on in the literature. Okay. So, in a slightly different vein, what we are also going to discuss, this out of equilibrium quantum many-body system, which this Raphael-Sorkin's model would be in our context, and the non-equilibrium regime is achieved by Quench in the system parameters, and that's what we are going to discuss. So this is a very interesting and important field of research today in many areas, not only in high energy, but also in condensed matter and various other subjects. And there are quite a few interesting experimental papers recently, in particular using cold atoms and optical lattices, where such things have actually been experimentally studied. For example, this is a paper, this Rajibul Islam is actually from Kolkata, he is now settled in Canada. He was the first author of this Nature paper, which experimentally detected this kind of entropies. And this is another paper from the Harvard group, another Harvard group, which also, well, it's not, Rajibul is not there, but by Marcus Greiner, which also made experimental studies of the Quench in cold atom systems, and they actually produced graphs, which is really incredible. So anyway, so just to very briefly recap, so how do we understand entanglement entropy? This is not in quantum field theory. If I say quantum field theory, Val will be the first person to object because this is only true in finite systems. So we have a state of a system described by a wave function. If it is a product states of two systems, then psi AB is psi A tensor psi B. If it is an entangled state, you cannot factorize the wave function in this fashion. And the density matrix is defined in the usual way, and you can define the reduced density matrix by tracing over either A or B, which gives the mixed state. And the von Neumann entropy is simply trace of rho A log rho A, which is given in terms of this expression, where Pi is at the eigenvalues of rho. This is absolutely standard textbook material. Again, I emphasize this is strictly true only for finite dimensional systems, not for relativistic quantum field theories. Okay. So, the time dependent correlation functions in such systems can describe the propagation of quantum information. And one of the things which is being studied quite a bit recently is what is known as out of time ordered correlators, or OTOCs, which is defined in this particular fashion. It was first introduced in a completely different context by Russian physicists in 1969, but it has gained prominence in recent years due to many reasons, including that coming from high energy physics, string theory, as well as in condensed matter theory. Okay. Okay, this I already said. So now let us come to the system that we are going to study. So first we studied an extremely simple system, which is a Hamiltonian of a many-body system given by this particular expression. So these are just bunch of coupled harmonic oscillators. This is as simple as a system can be. And this is exactly what Raphael-Sorkin studied, except that he did not have time dependence in these parameters. So the new thing that we are doing is to making these parameters omega and k explicitly time dependence, and then study the behavior of the system under various kind of time dependencies. So now the question is, so suppose you take case n equal to 2, that is really the simplest thing, and then Your Hamiltonian is just a two-body Hamiltonian, two coupled harmonic oscillators, which is related to the Bose-Hubbard model in certain contexts, but that's not so important for our purpose here. So, but this Hamiltonian, you can just go to the normal modes and then it completely decouples, right? You have two interacting harmonic oscillators, you go to normal modes and they completely decouple. So, once you have that, so what you want to do now is to solve a time dependent Schrodinger's equation given by this. This is our goal, to solve the time dependent Schrodinger's equation to begin with for this two body case. We will later go to the n body case. So, how would you do that? This thing has a very interesting history which I learned. So, in general, it's very, very difficult to solve such a time dependent problem where Hamiltonian is explicitly time dependent. If you want to analytically solve it exactly, it's very difficult. However, there are certain situations where you can find an invariant Hermitian operator which satisfies this equation. And if you can find such an invariant Hermitian operator, then knowing the eigenvalues of I, you can find the solutions of this equation. This was first discussed by Lewis and Riesenfeld in 1969, although I think there were previous papers by some Japanese groups indicating that. And okay, now how would you find an invariant operator? That is also not an easy task, but if H itself is an element of a dynamical algebra, then the task becomes simpler and this invariant operator can be written in terms of the elements of the dynamical algebra. So, for example, in the case of harmonic oscillator, the dynamical algebra is given by SU11. So, the Hamiltonian can be, the I can be written in terms of the elements of SU11 algebra and you can find a solution. So, I won't go very much into the detail of the derivation of the solution, but what was really at least eye-opener for me is that if you want to solve such a problem, let's say even for this extremely simple Hamiltonian, you can do so provided you can solve this particular equation. Okay? This is a complete miracle. So, look at this. This is a linear equation, linear Schrodinger's equation, where H is given by this expression, omega is time dependent. How will you find a solution to this? If you can solve this equation, which is called the Ermakov equation, which is a nonlinear differential equation, if you find this solution, then this psi here satisfies this. Now, how Ermakov discovered this equation, I really do not know. All his papers are written in Russian in the late 19th century. He was in Kiev in Ukraine doing this work. How he did it, I really couldn't figure it out. But this has become very, very popular these days among condensed matter physicists, some string theorists, high energy physicists, that whoever wants to study time dependent solutions to such problems, and this is not the only problem whose time dependent solution you can find with Ermakov, there are many others. Anyway, the bottom line is that we are going to, first we will solve such an equation and then we are going to derive the solution of the time dependent Schrodinger's equation. Okay. This is really okay, there are some very interesting mathematics behind it based on the representations of SU11, which is intimately related to that, but let's not go into that here. Sorry? No, B of t is what is going to be determined or found out by solving this equation. No, analytically. Numerically, I don't know how to do it. But for certain cases, you can do it analytically. That is the miraculous part. Well, for arbitrary omega t, you cannot do it. So, the point is, for those omega t's for which you can find a solution of this equation, for which you can find a solution of our Markov equation, you have the solution of the time dependent Schrödinger's equation. This is the point, okay? For if you give absolutely arbitrary thing, whether you can solve this, I don't know. But there are huge maths literature on this equation as to how, this is a nonlinear differential equation, right? So finding solutions, I mean, there are no general techniques of finding solutions of nonlinear differential equations. But there is something called nonlinear superposition principle. And I don't want to get into the details of all that. There are well-developed techniques using which you can actually find solutions of this equation for certain kind of time-dependent omega, okay? So we are going to restrict ourselves only to those cases, so very, very simple cases. So once you have a solution of the time-dependent Schrödinger's equation, you can write the wave function. These are just, mathematical expressions, nothing fancy in this. So it's some exponentials like the Gaussians and with some time-dependent phases. So now the reduced density so what happened to this? Okay. So the reduced density matrix can be calculated in the usual way. This is just straightforward calculation because you see there is nothing fancy going on. This is just Gaussian. So, sorry. Yeah.
I guess my question is related to the
right.
previous question. And maybe you already showed it, but what form of omega t did you use?
I am coming to that. I didn't show that. Right. I will show. So I am coming to that. See this, this equation is for that. Okay. I mean, if you can solve this equation, then this object satisfies this. We are doing for many degrees of freedom. Right, because see, what happens is, as I showed you, you decompose the system into normal modes. So once you decompose the system into normal modes, they are all independent, right? So you solve for each and then you go back.
So you do it for each normal mode separately?
Right.
Okay.
That's okay. That's kind of cheat. Well, it's not cheating, but it's a technique. So, okay. Anything else on this? All right. So I want to emphasize that the whole thing becomes computationally very simple because you have reduced your system to just normal modes and Gaussians, and we all know how to handle Gaussians. So that's what makes it tractable. Although, there are complicated time-dependent factors, but who cares about that? I mean, I'm just integrating on Gaussians. So, okay. So the reduced density matrix you can calculate by integrating out 1 degree of freedom. And again, this looks complicated, but there is nothing profound in these things. And the reduced density matrix, you can find the eigenvalues from this integral equation. These are all standard given in Raphael's paper, Srednicki's paper, etc. All that goes through except that the eigenvalues are now time dependent and the von Neumann entropy has this form. So now let's come to the examples. Okay. So to answer Sachin's question, so let's say we start with this particular situation. We are making a, Commute with what? Yeah, sure. That's not, No, see, this is a global quench. This is not a ramping. This is a global quench. And that we checked. Yeah, that works. There is no problem with that. Okay. Even for ramping, it works in some cases. That decoupling part is not an issue. Okay. So first we use a global quench where omega initial is omega and omega final is 0, just to give some examples. So in this particular case, the solutions of Armakov equations are given by this. So there are two normal modes. So two different B's, B1 and B2. B1 is this, B2 has an oscillatory behavior. where M1, M2 are given in terms of the system parameters. So now if you calculate the von Neumann entropy, recall that von Neumann entropy was given by this particular formula. All you have to do is to plug your solution in, and your von Neumann entropy as a function of time behaves like this. Now these oscillations are, coming because of the fact that you have explicitly time dependent cosine functions here. That is what is giving rise to these kind of oscillations, okay. Just as an example. So you can do it for many other kind of oscillations. So for example, suppose you go from omega bh initial to omega bh final for various kind of values, you can still find solutions in terms of the two normal modes. And so just to give you another example, suppose omega bh initial is 3 and omega bh finals are given by different values, so you will find different behaviors. So they are all coming, in this particular case it is easy to understand why these oscillations are coming. Again, it has to do with this type of behavior of B1 and B2, okay. So but our goal is not to solve the system for 2 degrees of freedom. We want to go to the thermodynamic limit and also use not this simple Quench protocol but other Quench protocols to unravel what could possibly happen in quantum information scrambling. Okay. So again, these are various examples for simple systems in for 2 degrees of freedom, and you see a typical behavior like this. Okay. So now we really want to study the system for arbitrary n, okay. Now you can do the whole calculation analytically for arbitrary n. There is no problem for that, because at the end of the day you decompose into n normal modes, you solve for each one independently and then you go back. So that's a pretty straightforward thing to do. So you can write it in some matrix form. The Hamiltonian has this you can write it in this particular way. And then again you can solve this equation, the time dependent Schrödinger's equation, whose solution will be in terms of the Armakovs, but now there are typically n different solutions of n Armakov equations. It may happen that for certain cases 1 or 2 solutions may match, but in general you have n independent solutions of n Armakov equations, in terms of which you can find the solution of the time dependent Schrödinger's equation for n coupled harmonic oscillators. Okay. And typically the solutions of Armakov equations, these are the normal mode frequencies which have this particular form, and we choose initial conditions as the ground state of the time dependent pre-quenched Hamiltonian of the n oscillator chain which requires B01 and B dot 0 equal to 0. So basically we are solving some time dependent differential equation, and these are the boundary conditions for that. So now we don't simply want to solve with a simple quench. So what we did was to make a series of quenches. Now I want to emphasize that this series does not go to infinity for us. This is not a Floquet system we are solving. For Floquet, people have done many calculations. The physics is completely different for Floquet. This is not a Floquet system. This number of quenches are going to end at some point. It could be 3, it could be 5, and so on. Of course, we could carry this on to infinity analytically. That's not an issue, but that's not an issue as far as calculation is concerned. But for physics wise, the answers could be different. Okay. So let's say we are quenching from omega initial equal to 3 to omega final equal to 20, and suppose these gaps are, let's say, 4 seconds. It could be anything. It could be 4 seconds, 400 seconds, 40 seconds, doesn't matter. I mean, you could solve the whole thing analytically. So I won't, you do this calculation, it's just a generalization of the previous calculation, nothing more than that. And you can calculate the reduced density matrix. reduced density matrix has this particular form. And note that the ratio, this is an important point, the ratio between the diagonal and a generic off-diagonal reduced density matrix can be written in this particular way. Now, why is this important? See, for a single quench, let's say for n equal to 20, so green line corresponds to n equal to 20, blue line corresponds to n equal to 500. These parameters, gamma minus beta and gamma, behave like this for a single quench, you see. But now notice what happens in a multiple quench. So suppose you have the same thing, n equal to 20 at n equal to 500. If you make multiple quenches, then gamma minus beta and gamma behave in a different way. You see, this gamma minus beta and gamma, particularly gamma, has picked up a much higher value. Here gamma was something like, in this particular example, maybe around 30. Here it has become close to 5,000. Now what, yeah.
When you have many oscillators, you have many normal modes,
Correct.
right? So I don't know if you already said this, but which frequency are you quenching?
All of them.
All of them,
Right.
every
Yeah,
and
yeah.
they are all not necessarily the same, but nevertheless you're quenching
That's right.
all of them
so,
by the.
see, each normal mode frequency would be determined in terms of the original system parameters.
That's right.
So, I am quenching on the original system parameters, and therefore, I am quenching on all normal mode frequencies. Okay. So, now why am I emphasizing this point that gamma becomes large for multiple quench? Because if you go back here, you see as gamma becomes large, this ratio becomes very, very small. So, essentially how should I say, the reduced density matrix is becoming more and more diagonal. So, the off diagonal terms are getting dropped off as n becomes large and number of quenches are becoming large. So, that is, I am not claiming anything about thermalization, but that is typically what happens when you are approaching thermalization, that the off diagonal terms starts to become smaller in the reduced density matrix and diagonal terms tend to dominate. Okay. So, now for the entanglement entropy, again you see, although this is a completely integrable system, absolutely integrable, at least naively integrable system, the entanglement entropy saturates. It saturates pretty fast, which is also a little bit different compared to, if you compare here the entanglement entropy did not saturate, it is keeping on oscillating. Whereas once you start to go to the thermodynamic limit and you look at various, if you increase n, let's say we considered 500, you could take even larger, and you start to increase the number of quenches, you see that these objects saturate, which is again an indication that this completely integrable system is sort of equilibrating, which is very, very counterintuitive. Such integrable systems do not normally equilibrate. I am not making any statement about thermalization because we have not done any analysis of thermalization, but it is beginning to equilibrate. That means things are becoming time independent, which is not expected in a usual integrable system. So, the same thing happens for momentum distribution, the similar conclusions you can gain from that. Okay. So, now let us come to the information scrambling. So, the OTOC between two, I should have written local operators m and n separated by a lattice distance L, this is the standard definition. So, if you expand this object, you will see that this is not time ordered. That is why there are some terms for which are time ordered, some terms are not. That is why it is called out of time ordered correlators. And we have chosen extremely simple operators, m as xi, mi as xi and nj as pj0. So, very, very simple thing. So, For well separated local operators, which we have, the OTOC starts from a 0 value and then increases as the information propagates with the Lieb-Robinson velocity, right? This is the standard thing. And again, from our intuition in integrable systems, we would imagine that the information cannot get scrambled, should not get scrambled in an integrable system. So therefore, OTAC should be oscillating. It should not be saturating. That is what our intuition tells us. So you can again do this calculation analytically. It's a long calculation, but it's possible to do using the ARMA curves. These expressions don't tell you much, but these figures might. So look at this situation where
Kumar, you have 10 minutes.
Yeah, I'll be done in 10 minutes. So look at this situation where n is 500 and we have considered 3 quenches, 3 situations. Green is just 1 quench, red is 3 quenches, this purple is 5 quenches, n equal to 500. And you see what is happening. So for 1 quench, OTOC will keep on oscillating like this, which is what you expect in an integrable model. For 3 quenches, it is still oscillating but less. These dips are less than these green ones. And for 5 quenches, it's even less. So if you push this up to 9 quenches, 20 quenches, this guy is going to become more and more flat, which was really completely unexpected, at least to us. There is no intuition that tells you that in an integrable system, OTOC would behave like this. In other words, the information would be scrambling. You would expect that it will come back to 0 because it's not going to get scrambled. But that is exactly what is happening. Okay? Now, look at this situation. So here, recall here that I fixed n equal to 500 and I considered these 3 quenches. The next one, I fixed the number of quenches to be 5, but I considered different number of degrees of freedom. And again the same thing happens. If n is 20, which is far away from the thermodynamic limit, OTOC starts to oscillate, dips. And as you increase n is 100, the dips are less, n is 500, it's more or less flat. So the bottom line is that if you remember, I emphasize this is a completely trivially integrable system. But still, even in this simple trivial case, if you go to the thermodynamic limit, n equal to 500 is thermodynamic limit for all practical purposes. And if you increase the number of quenches, the system seems to equilibrate. Okay? This is what we found to be utterly puzzling. But later we found that now this kind of behavior for integrable systems is being discussed by many people, and in particular, let's say by Alba and Calabrese and those people who have found that for systems which are integrable and yet solvable by Bethe ansatz, there is a particular kind of thermalization that can occur. This is called eigenstate thermalization. It's not full eigenstate thermalization, but a particular type of eigenstate thermalization can happen for such examples. And we found that for harmonic oscillator, very strangely, this was discussed in the 1940s by Bogolubov. He called something as transient chaos. And in particular, I think his student Cherkov and later Israelev, they all discussed this situation, which is called transient chaos, where this kind of behavior can happen. Bogolubov explicitly mentioned it. I don't know how he found it out, but he explicitly mentioned it. So it seems that the question of how or whether a system will thermalize and its relation to integrability is not as straightforward, at least in the quantum case, as one might think. In classical case, perhaps it's easier, but in quantum case, there are many subtleties. So I come to my summary. So I'm not going to read this out again. Essentially, the the model that Sorkin proposed, which is a very, very simple model from which he could extract properties of black hole entropy. To the extent his conclusions are true, to that extent, our analysis also provides the behavior of at least this kind of quantum fields on that black hole background. So how the time dependence will, how the time dependence of entropy or the OTOC will should be observed in such backgrounds is described by this analysis. To the extent his analysis is applicable to the black hole entropy. And so I guess there are many other things one could do with this. Lot of people have now picked up these multiple quenches, and in circuit complexity, a lot of people are now studying these multiple quenches, and they are finding quite interesting answer in several IIT group. We know groups which are doing this. So that's it. Thanks.
Questions?
I don't know if it's like it can be called from order to chaos transition or something like that based on your parameter quenches. But my question is like, so is this generic for any parameter, or is there any specific value of quenches or specific frequency?
No, this is generic for.
This is generic for all omegas.
Of course, as you see here, in the two particle case, it's easy to understand because the expressions are simple.
Right.
So you see there are different parameters that we are taking, and whether it is oscillating or this guy is also going to oscillate. It's just period is bigger.
Right.
Okay?
Right.
So
right.
this behavior is generic for any parameters. Any set of parameters. Okay, if you chase very pathological thing, there may be some corner of the parameter space where something funny might happen.
Right.
But generically, typically this is going to happen.
That's very surprising.
Yeah,
is it the quench that makes it quench rate that makes it the integrable to chaotic?
Okay, we didn't calculate the effect of the quench rate because we fixed it at that t equal to 4 seconds.
Right.
But what makes the difference is the thermodynamic limit and the number of quenches. The quench rate part we did not check, but
Right.
it can be easily checked. Okay?
Nice. Okay, thanks.
And for the ramping also, it's possible to do. If you do the multiple ramping, but you put in some, let's say, very arbitrary, very ad hoc quenches in between the ramping, then also this kind of thing can happen. This ramping part was being analyzed by Shumit Das and his collaborators.
Tenjo?
Yeah, I may have missed what you meant precisely by a quench, but how is the quench integrable?
The quench is integrable because of the Tarmakov. So, it's exactly solvable. It's not just integrable. You can. So this omega is what is being quenched. Okay.
Yes.
So omega, let's say t less than 0 is 1, t greater than 0 is 2, for example. So that's a quench. That's a sudden global quench. That's what is called a sudden global quench. Now, why is it exactly solvable? Because for that time dependence of omega, you can solve the time dependent Schrödinger's equation.
Solvable and integrable aren't the same.
Okay, it's integrable. It's a harmonic oscillator, right? How I would like to know how it breaks integrability, but I couldn't find it.
Our integrability has conserved quantities.
It does.
So are the quantities conserved through the quench?
So before the quench and after the quench, it's just harmonic oscillator. It's a sudden global quench, right?
So presumably they are not the same.
But they are there.
The constants of motion shouldn't be there.
They're different, but they are there.
Then it's not integrable.
Okay, fine. But people call this integrable also. I don't know. I honestly don't know the terminology, but this is typically what, in fact, I don't know the details, but typically this is considered as a paradigm of integrability.
I guess the point is that something can be solvable and not be integrable. I think that
perhaps it can be. But at least for this kind of system, even if it is not integrable, you see, the point is that when you have small number of particles and just a single quench, it shows in terms of equilibration, it shows all the behavior of an integrable system. But when you go to the other case, here, when your number increases to the thermodynamic limit and the number of quench increases, it shows the behavior of an equilibrating system. So this is for sure, this is just calculation. Whether you call it integrable or anything else, it's a terminology. But this difference of behavior is there.
Other questions? Oh, Bal has a question.
Yes,
This is not exactly what you're doing here,
right.
but I think it is somehow related. In QCD, let us say, the generic quantum state in the colored state, okay, is necessarily entangled. Okay?
Yes.
This can be proved, okay, and we have proved it. Okay, now it happens that the Hamiltonian of the system, there is some non-abelian chemical potential I talked about earlier, and it changes this entanglement as a function of time, and consequently also if you compute entropy, this entanglement is, I would say it's a classical entanglement, okay? And as you change as you look at the time evolution, for a set of particular chemical potentials, it oscillates like this.
Oh,
Exactly.
I see.
Yeah. But for some other orbits, okay, this entanglement is ergodic. Okay?
I see.
It goes ergodically through all possible entanglements that you can imagine. Okay?
Okay.
I think that this is related to the phenomenon you are finding in finite dimensions.
That very well could be. That's an extremely interesting thing that you said. I didn't know that it can oscillate in such cases. But here, you see, here the system being analytically so trivial, it's kind of easy to understand where the oscillations are coming from. They're simply coming from the n normal mode, Armakovs for the n normal modes, which have this oscillatory behavior.
One small thing. With respect to solvability and integrability, actually in the harmonic oscillator problem at least, it was shown by Padmanabhan or Paddy that there is this Yermakov-Lewis invariant which commutes with the Hamiltonian.
Right,
So that there is some conserved quantity
right.
which is kind of thing which is needed for integrability. That is what is the issue.
See, that is what I said at the very beginning here. So, you are absolutely right. I mean, the way you solve, how are you going to solve this guy? It's not an easy thing to solve. So, you have to first find an invariant, this I, and which didt is 0. Okay? So, if you can find the invariant in terms of the eigenvalues of that, you can find the solutions of the harmonic, the Hamiltonian. And that is where okay, this is general, this is completely general, and for harmonic oscillator or let us say Hamiltonian, for which SE11 is the spectrum generating algebra, for that the Armakov comes. So there are a whole lot of models, you can do Calogero models, you can do harmonic oscillator, you can do many things for which this Armakov guy shows up. Thank you.